My name is Paul McEwen, and I'm a professor here in the physics department at Cornell University. And I have a really distinct honor and pleasure of telling you just a few things about two of my scientific heroes. So the first, of course, is Hans Bethe, for whom this lecture is named. Now, Bethe was undeniably one of the most brilliant physicists of the last 100 years. He, for example, taught us how the sun works. I mean, that's pretty good to figure out how the sun works, how it makes energy. And for that, he won the 1967 Nobel Prize. But that's really only one of a wild number of things that Hans Bethe did over his scientific career. As another very famous astrophysicist, John Bacall, once said, "If you know his work, you might be inclined to think he is really several people, all of whom are engaged in a conspiracy to sign their work with the same name." It was amazing what he did. But what's even more amazing is that his scientific accomplishments are only a small part of the story of Hans Bethe. He also made this department what it is in so many different ways. So the man who understood how the sun worked also cared very deeply about people and about his society. Though he helped give birth to nuclear weapons, he also argued strenuously against their indiscriminate and inappropriate use. And he also set a tone of conduct for our department that extends down to the generations today. He was obviously smarter than the rest of us, so how could we be jerks if he was such a good guy? So he was really the whole package: scientist, citizen, leader, and role model. And it's a fantastic thing that once a year we get to have the Bethe Lectures to honor his memory. So that brings us to our second hero, our speaker today, Paul Alivisatos, who is a professor of chemistry at UC Berkeley. Now, Paul, like Hans, is a very distinguished scientist, a member of the National Academy of Sciences, for example, and with many more awards than you want me to name here right now. He has been the leader in the field of nanocrystal science and technology for a quarter of a century and has really set the agenda for that field decade after decade. But in addition to that, since 2009, he's been something else. He's been the director of Lawrence Berkeley National Laboratories, which it puts him in charge of something like 4,000 scientists, engineers, and staff people. Now, taking on a job like that is something like going into a torture chamber if you're a scientist. Am I right? Yeah. I think he's not allowed to say, but it's true. Long meetings replace experiments. Trips to Washington replace time spent with your students. So why would you do something like that? Why would you take on a job like that? This is a very good question. And the answer is because Paul, like Hans Bethe before him, is not just a great scientist. He is also a great citizen and leader. And with his colleagues at Lawrence Berkeley National Labs, Paul's goal is to change the way we power our planet. He dreams big. Through initiatives such as Carbon Cycle 2.0, which he's going to tell us about here, Paul is trying to change everything in how we do things. And just as Hans Bethe taught us what powers the sun, Paul and his colleagues are trying to tell us how to use the sun to power our world. So please join me in welcoming the 2011 Bethe Lecturer, Paul Alivisatos.
Thank you, Paul, for those very kind words and for that very nice introduction. And it's a really great honor to have the opportunity to speak in a lecture that is dedicated to the memory of such a great physicist as Hans Bethe. And in thinking about the preparation for this lecture, certainly my goal for this public lecture was from the beginning, from the moment I was invited, I thought, well, I need to talk about some way in which we see the great issues of the day, what really is one of the biggest issues that faces humankind, and to try to address how physics addresses that issue today in a timely manner. Now, certainly at Berkeley Lab, as a national laboratory, it's also our job to try to think hard about how this institution, it's a storied institution with a great legacy, it's important for us to think hard about what should this institution really dedicate itself to. And really over the last several years, Berkeley Lab has reoriented itself to address what we think is one of the greatest issues that face the planet, and that is the imbalance in the carbon cycle. And today, I would like to talk with you about this imbalance, and I'm going to start my talk by going through actually the history a little bit of how physics evolved over a period of a little over 150 years in such a way as to provide the framework for us to actually understand the global warming problem. So that's going to be how we start, and then I'll give you some of the specific aspects. Now, first of all, let's recognize what we would think of as carbon cycle 1.0, and that is a planet in which carbon cycles around in terms of all different phenomena that might occur. For example, plants decay, and there are volcanoes that will spew molten rock and then therefore CO2 out into the atmosphere, which can return into the ocean and then form sediments and then cycle again over very long periods of time. And there's a biological cycle that's going on. And carbon is cycling around. And if we look at the period from 50,000 BC to just before the steam engine, then we can recognize a period in which the net change in carbon in the atmosphere is actually quite small. Today, with human activity, as I'll be showing you momentarily, actually the net flux of carbon into the atmosphere each year is about 100 times that natural geological flux, which takes place from volcanoes and other such things. Of course, the biosphere rapidly exchanges carbon on a vast scale, larger even than the scale at which people emit CO2 into the atmosphere. But the biosphere itself is typically net neutral, no extra carbon in. So when we put extra carbon into the atmosphere, as we have been, the only way ultimately in the long term to restore it is through the geological cycle, which of course takes a very, very long time. So we've knocked it out of balance, and of course the goal of the Carbon Cycle 2.0 initiative is to provide a science basis which would allow us to have good well-being for people in the developing world to have the opportunity to have a good economy and health, but at the same time to restore the balance of the carbon cycle on a global scale. So let's work our way through a little bit of the history. Our topic for today is the concentration of CO2 in the atmosphere and how it has changed and how we could change it back. So this just shows the concentration of CO2 in the atmosphere over a period of time from the year 1000 to say the year 1600. You can see that it was invariant. It really wasn't changing. And then all of a sudden it takes off. And here you can see, it takes off. Okay? Now you could say, well, what happened in this year? Well, what happened in that year was the discovery of the first practical steam engine, the first steam engine that could actually be deployed in a way that could be widely used. Now, what did that engender? Of course, the invention of the steam engine engendered an incredible level of new economic development, the Industrial Revolution. It also stimulated science. And you know what science it created. It first created the science of thermodynamics. And so we're going to look at that momentarily. Today, I'm going to try to just quickly go through these three questions. Does an increase in atmospheric CO2 influence the Earth's temperature? You might say, well, why am I going to belabor that point? Well, I think it's a point that people need to be reminded of, and I'm going to show you the underlying physics of it. Is CO2 increasing? And is that increase due to human activity? We'll just review the evidence. And then we'll try to look at this question. Can't we simply adapt to any changes that might arise from the CO2 changing? Can't we just adapt to that? How big is the effect? So we'll see. Okay. And for a start, we're going to go back all the way to the 19th century, and we're going to look at the science of these three scientists, Fourier, Tyndall, and Arrhenius, in the 1820s, 1860s, and the very end of the 19th century. We're going to look at the science from those three scientists. And we'll start with Fourier. And I mentioned to you a moment ago, just after the steam engine was invented is when we started to see the CO2 going up. And just after the steam engine, physicists invented thermodynamics because they were trying to understand how steam engines work. So Fourier, who's probably well known to many of the scientists in the room, did all kinds of important mathematics, but actually what he developed that mathematics for, more than anything else, was in order to develop a theory of heat and radiative transfer. In other words, if you have a hot and cold body and they're in contact with each other, how does heat flow between them? Or let's say that you have a very hot body that's very bright, and then a colder body over here that's dark. How, through light, does energy get transferred from one to the other? So he was trying to study that problem and developing the mathematics and the theoretical physics behind what at that time was one of the great problems of the day. And he decided to take up one of the classic problems, which is to calculate the temperature of the Earth. So you have the sun, it's glowing, it's bright, it's hot, it clearly warms the Earth. The Earth is sitting otherwise in a very, very cold environment. And what establishes the temperature of the Earth is, of course, that sunlight comes and hits the Earth and warms it, and the Earth in turn re-radiates energy out into the atmosphere, into the universe at a lower temperature than the sun. And if you balance out all of the heat in and the heat out, you should be able to calculate the temperature. He's a very good physicist. He did mathematics beautifully. He calculated the temperature, and it came out minus 18 degrees C. And clearly, the temperature is not minus 18 degrees C. And every way that they could check the theory of heat transfer, it still came out minus 18 degrees C. Whereupon it became clear that something was missing from the model. And he theorized that without a lot of the underlying science needed, but he intuited that what was needed was to know that there is an atmosphere. And he describes that here. He says, the heat of the sun arriving in the form of visible light penetrates transparent solid or liquid substances, but loses this ability almost completely when it is converted with the terrestrial body into dark radiant heat. And so what he's saying is basically incoming visible light passes through the atmosphere, makes the Earth warm, but then the light that is emitted subsequently, infrared light at longer wavelength, is actually reabsorbed by the atmosphere and radiated back towards the planet. And he understood that something like that was going on, and that atmosphere was acting as a blanket that raised the temperature of the Earth. So that's the first discovery. But of course, at that time, there would have been no way to know what it was in the atmosphere that caused the infrared light to be absorbed. That people couldn't know at that point in time. And in fact, that waited for the development of another incredibly important field, which is the field of spectroscopy, the interaction of radiation with matter, systematically studied. And that took also quite some time to develop and really didn't become sophisticated as a field until well into the 20th century. But nonetheless, the early observations was to study infrared absorption of gases, which is what John Tyndall was doing. He had a way to create infrared radiation and was able to pass it through a series of different gases and was able to see that a gas which was transparent to visible light could indeed absorb infrared light. And he studied that, and he found that water absorbed light, as did carbon dioxide. And here we just simply show the two vibrations of carbon dioxide that are characteristic that we know exist today. And Tyndall, when he studied the infrared absorption of water and of CO2, immediately recognized that this could be physically the mechanism by which the Earth traps the heat. So the visible sunlight comes in and is absorbed by the Earth, which then radiates infrared light outwards. And of course, if there's a layer of gas surrounding the planet, that absorbs the infrared radiation, and some of it is radiated back down again, so that the Earth gets radiated twice, once by the visible light and a second time by the re-radiated infrared, and that, of course, raises the temperature of the Earth and ultimately can lead to a calculation that is consistent with the Earth's temperature that wasn't present in the first version. And that's described in this kind of poetic literature that was used at that time as a dam built across a river causes a local deepening of the stream. So our atmosphere, thrown as a barrier across the terrestrial rays, produces a local heightening of the temperature at the Earth's surface. Without water, the Earth's surface would be held fast in the iron grip of frost. Okay? And indeed, it's not just water. Of course, he recognized immediately himself that CO2 also played a key role. And you can see that a little bit here because you can see this mode of the CO2 in kind of a window of the water. So the water is going to absorb a lot. And of course, there's a lot more water than CO2 in the atmosphere. But nonetheless, there's critical vibrations of the CO2 which fill in holes in the infrared spectrum of the water. And as you'll see in a minute, although water is very, very important for the temperature of the Earth without question, CO2 is in a sense a control knob, and we're going to see that in a moment. The next key development in this field is due to a chemist named Svante Arrhenius. And Arrhenius is famous to all chemists because he discovered the laws of kinetics, that he won the Nobel Prize for developing the equation that describes the barrier that prevents a chemical reaction from occurring, and developing the equation which correctly describes the temperature dependence for how chemical reactions, for example, vary with temperature. And he had a friend in the Swedish Academy who was a geologist and whose research activity involved trying to understand what caused the ice ages. And the theory that the geologists were tossing around at the time was that perhaps some kind of a change in the carbon dioxide concentration in the atmosphere had caused the changes in the temperature of the Earth that led to the ice ages. And Arrhenius got very interested in this, and he decided to perform a calculation. And what he did is he said, okay, I'm going to take carbon dioxide that's in the atmosphere. First of all, he measured the carbon dioxide in the atmosphere, which was a very tricky measurement. He actually used reflected light from the moon. It's a whole story. In any case, he did get a good measurement of the concentration of CO2 in the atmosphere. And then he said, okay, well, what would happen if, in fact, all of a sudden, the CO2 in the atmosphere was cut in half? And he calculated the temperature. But while he was at it, he also, while he was doing these calculations, noticed that all these factories were around, and he actually writes in his paper, in the 1896 paper, that he thought, okay, since they're all emitting CO2, he would just calculate not only what would happen if you cut it in half, but what would happen also if you doubled the amount of CO2 in the atmosphere. He just thought, I'll calculate what would the effect of that be. Now, it turns out that he was definitely performing that calculation without all of the necessary theoretical tools that existed maybe 30 years after that, okay? But nonetheless, he was able to make an estimate, and his calculation says if you double CO2 in the atmosphere, the temperature will go up in his first calculation by 5.1 degrees C, okay? And immediately he also realized, but hey, if the temperature goes up by that much, it'll put some more water that will vaporize from the oceans into the atmosphere. So it'll put some more water in there, which also acts as a greenhouse gas. That'll be a positive feedback, but there are also some negative feedbacks. He tried to do his best estimates, and he did another calculation about 5 years later, and he got 2.1 degrees C. Actually, today, the best calculations that people know how to do is maybe 3.5 or so degrees C. So not bad for Mr. Arrhenius with what he was working with. It's also very interesting, a couple other things about this famous 1896 paper. One is that he thought to himself, well, okay, there's this industrial revolution and there's a lot of carbon dioxide going into the atmosphere. And he thought, you know, it wouldn't be so bad because Sweden could become a lot more productive in its agriculture if the temperature went up a lot. But he also performs a calculation at the end of the paper and says, okay, let's just see if this is plausible that CO2 could double. And in his paper, he concluded, no, the rate at which factories are being formed is simply not sufficient that enough CO2 could be put into the atmosphere to double it. And of course, that was under certain assumptions about how much growth would take place. And in fact, economic activity has been increasingly increasing. And so his estimate actually of 2x is actually very apropos and is a topic that is discussed. And ultimately, due to the 1896 paper, what will happen to the temperature of the Earth when there is a doubling of the CO2 in the atmosphere is known as the climate sensitivity, and is of course something which people are deeply occupied with and trying to understand. This was a seminal paper. In fact, this was, in a sense, the breakthrough paper in this field in its entire history. Now today, of course, we know a lot more about these things, and here you can see the black body radiation from the sun, the black body radiation from the Earth for different temperatures, and here we see the total absorption and scattering of the atmosphere, as well as the key gases, specifically, most importantly, looking at water vapor and at carbon dioxide. Now, one thing that you will notice here is that these absorption lines due to the water or due to the carbon dioxide are highly, highly saturated in the sense that the absorption has taken place to a very high degree. And if all we had to deal with was a very simple oscillator model of molecules absorbing light, then those lines would be relatively sharp lines. But as you know, the absorption of light due to the vibrations actually has pressure broadening, but also broadening due to the rotational transitions that couple in with them. And the lines have enormous width to them, okay? And so you can saturate the center parts, but there are long wings in those absorption spectra that play a big role in this story. You can also see right here the CO2 fitting right in there in that hole, and that, of course, is a very key part of the story of the calculations of the temperature. This graph shows a one-level deeper understanding, and this is going to be slightly technical, but it will be brief. This shows the black body radiation as calculated from a model of the Earth's atmosphere. This blue curve is as calculated. This dip here comes from the CO2 in the atmosphere. So this is infrared light emitted by the planet as it tries to cool itself. This is absorption from the CO2. The red curve here is the measured number, this one and this one, from two different satellites. And the blue curve is, of course, the calculated number. And you can see it's a black body, but there are these strong regions of absorption due to CO2 or to water that are extremely, and ozone, which are extremely, extremely important. And you'll notice this big fat line here, which of course comes from the broadening of the level. Now, there's one more thing to remember. Just after Arrhenius published his paper, about 5 years later, there was a paper written by somebody named Ångström. Now, you'll all know the name angstrom because that's one of the units of distance. Today, it's largely eclipsed by the nanometer, but it's 1/10 of a nanometer, and it's a very famous unit. And Ångström's son was a physicist who replied to Arrhenius saying, you know what, I think you're wrong because all of these absorptions are going to be completely saturated. And I told you already about the wings. That's one thing to remember. But there's another very, very important thing which you can't quite understand the picture of how the temperature of the Earth is determined unless you know this one additional feature, which is the following. When infrared light is emitted, it gets absorbed, and then it can be re-emitted downwards or upwards, and then it can be reabsorbed again, downwards, upwards, and so on. But eventually, at some height above the Earth, the atmosphere has become thin enough and the amount of that gas is sparse enough that that last layer, the very last layer, emits without having saturation, okay? Because there's not much gas above it anymore. And that's the one which loses most of the heat and which does most of the cooling, that last layer. But as you put more, what you need to also know is that the temperature is dropping as you go up higher in altitude. So now, as you put more CO2 into the atmosphere, the height at which the last photons escape goes up higher and higher in altitude, therefore is occurring at a lower and lower temperature. And therefore, you're cooling the planet a little bit, but from a lower temperature, and therefore, everything gets warmer. Okay? What that means is, if you put more CO2 in, even when the line is saturated, because the final temperature at which the radiation escapes is lower, what that means is it's less effective at cooling, and therefore the planet below gets warmer. That's why, even though it's nominally saturated, you still have a very strong effect as you put more CO2 into the atmosphere. And that's the physics of why CO2 warms the planet. And it's very important for you to know that it's deeply tied with the history of how physics developed. Thermodynamics, spectroscopy, statistical mechanics, kinetics, quantum mechanics, all of those things play a role. And at every point in time, actually, the more you trace the history, the more you see it. At every point in time, the moment a new theoretical physical tool was developed, a short while later, its implications for how it controls the temperature of the planet was very soon realized, after some debating in many cases, but very soon realized. Now, I've mentioned to you CO2 as a control knob, and this is the last kind of thing I'll say about this, which is simply, here's a recent simulation, it's from 2010, and it simply says, let's perform a computer exercise in which we pull all the CO2 out of the atmosphere abruptly. Okay? So they just said, okay, here's planet Earth, it's equilibrated in the computer model that has all of these effects that I've described in it in there, and they just, at one moment in time on the computer you can do this, they just removed all the CO2, and they saw what happened. And what happened is the temperature drops very, very quickly, as we would expect, and goes down into a so-called snowball Earth. In other words, everything freezes. And you know, many people would say, well, look, there's all this greenhouse gas that's there due to the water. Wouldn't water be the important feature here, and wouldn't water just warm the planet? But the fact is, there's a big difference between CO2 and water, which is in the relevant temperature regime, water actually condenses. So if the temperature goes down enough, the water starts to condense. Then once it's condensed, it's not a greenhouse gas anymore because it's not in the atmosphere. And so that's why CO2 is the control knob, because it sits in that little window of water, which is a very key one, but also at the same time, it doesn't condense into a liquid at any of the relevant temperatures. And therefore, it's an incredibly important gas in ultimately determining what the temperature of the Earth is. And what I've just described to you is in no way controversial within the community of people that study the physics of the planet. And therefore, it's very easy to answer this question. Does an increase in atmospheric CO2 influence the Earth's temperature? The answer to that is an unambiguous, certain, definite, absolute yes. Okay? Now, the next question, is CO2 increasing, and is that increase due to human activity? Yes, it is, as you shall see. This shows the Keeling curve. Many of you may have heard of it. Keeling set out in the year of the year of geology, the year of the Earth, 1957. He established the first measurement at the peak of Mauna Loa. That's a site which is picked because it's at a high altitude and it's got appropriate, at that point all the gases have mixed in the planet, so when you look up above from there you can get an accurate measurement of the atmospheric carbon dioxide. It was established by him originally in that one site. And he started to measure at that time the amount of atmospheric CO2 because up until that point, people had been debating this question of will CO2 increase and is an increase in CO2 going to influence the temperature? And he decided, look, I'm just going to go and measure it, okay? And what did he see? Well, this measurement has now been going on all these years in between, and this shows the increase in the level of CO2. The average level of CO2 is that red curve as a function of the time. But you see these oscillations. And of course, these oscillations have to do with the difference in the planet's CO2 due to the temperature change each year when you go from summer to winter. Okay? And in the summertime, there's a lot more photosynthesis. A lot of carbon dioxide gets taken up into plants. In the winter, a lot of it gets released. So you can kind of see the planet breathing a little bit there. and you can see the increase. And what you can see is something that I mentioned kind of at the very beginning, namely that the biosphere changes due to what's going on in the biosphere are quite large numbers compared to the increases each year of what we're putting into the atmosphere. Okay? They are quite large numbers, but nonetheless, the numbers that we're putting in are all going in one direction, and the biosphere actually equilibrates over any given cycle. Now, it does turn out that Keeling also, not just Angstrom, but Keeling also had a wonderful son, and his son decided, Roger, to go off and study oxygen. Because one question we would like to ask is where is all that CO2 coming from and where is it going? And so we can just say, okay, let's assume that the CO2 that's coming into the atmosphere comes from combustion of fossil fuel. So let's just take an example of some type of hydrocarbon, CHN, and react it with oxygen. This is what we would do, is say these two will react to make CO2 and a certain amount of water. And so the CO2, if it came from the combustion process, then it means when we took the hydrocarbon and dug it out of the ground and burned it, we consumed some oxygen. This is our stoichiometry. One equivalent of O2 will be taken out of the atmosphere every time that happens. That's got to happen. So if CO2 is going up, oxygen has to be going down. So Keeling 2 went and measured the oxygen going down. And here again you can see the planet breathing, but you can also see the oxygen going down. Now this is a much shorter curve. It only started in, I think, the late 80s. Here it shows 1990, but I think it started in the late 80s. So it's a more recent curve. But actually, if you take this curve, now it's starting, just to remind you, of course, no need to worry, the amount by which the CO2 is going up is in the tens of parts per million, and the oxygen concentration is 20%. So there's a lot of oxygen there, but nonetheless, on that 20% base, it's going down. And it's going down because every time the chemical reaction of combustion takes place, it consumes some oxygen, and you can see it. You can measure it on a planetary level. That's the second Keeling curve, and it's kind of, I think, a definitive indication that there's a balancing of the chemical reaction that's going on. Another way in which we can have a strong feeling that fossil fuel is really what's responsible for this change is the change in the amount of isotope of carbon in the atmosphere. When plants do photosynthesis, they selectively assimilate lighter isotopes. That means they concentrate carbon-12 in them when they do photosynthesis. And so the oil in the ground, which was formed from plant matter, is actually enhanced in carbon-12 compared to carbon-13. And so therefore you would predict that if the CO2 going into the atmosphere is coming from the combustion of fossil fuel, then we would expect to see that there's a change in the isotope composition corresponding ultimately to putting more carbon-12 back into the atmosphere. And that's what you see here very clearly in exact proportion to what we see with the increase in the CO2 is that change in the isotopic composition. Now you might say, why don't you use carbon-14? And it turns out that people would love to use carbon-14 for it. The only problem is that when the nuclear tests in the atmosphere took place some decades ago, they put a lot of extra carbon-14 into the atmosphere, which has made it very difficult to use that isotope. Before that time, if you look at data, you can make sense of it, but afterwards, you can't do that. One additional thing to say to you here is we can now look at CO2 over a long period of time. I just showed you the Keeling curve, which showed CO2 going up in this interval. That's what I just showed you. But what about CO2 before that? I showed you the curve at the very beginning of year 1000 to 1800 or so. This is the curve back to 800,000 BC, and this is the CO2 over time, okay? And this is the CO2 now, okay? And so you can see that what's gone on in this last very, very, very short period of time of a couple hundred years is different than what happened during this entire period. Here you can see the ice ages, and you can see you enter and exit from them at slightly different rates. You kind of go up fast and down slow in CO2, and that's interesting, of course, to see that. But the fact is that all of those excursions over 800,000 years never look as different than that one period that is our period. Okay? And so that's what that is. Now, another thing to notice is the abruptness of this curve. And I just want to blow that up a little bit. This is one of those rises which is as fast a response as we ever see in the CO2 during natural periods. Okay? That's the CO2 going up in a certain period. That's a warming period. And here you can see it in this recent period. And what you can see is the time scale on which the CO2 is changing now is just a different time scale than any that has been seen. And what that also does is it worries a lot of people because, as many of you will recognize, when you have a complex system, it has a frequency response, a time response to it. And when you push it at a very fast time scale, it can respond differently than it does when you push it on a slow time scale. And we don't know what happens when you push the only planet we live on at a very fast time scale. So, we answered the question, would an increase in CO2 influence the Earth's temperature? Definitely. Is CO2 increasing? Yes. Is that increase due to human activity? Yes. About half of the CO2 that we put into the atmosphere every year stays in the atmosphere. Half of it goes into the oceans and the land. And that half that stays up there is, in fact, increasing the amount of CO2 in the atmosphere. And therefore, sooner or later, the temperature of the Earth is going to go up. That's the physics. Can't we simply adapt to any changes that might arise? We'll see the answer to that is a little less clear. Okay? But here you can see the measurements of the temperature of the Earth as a function of the time, going back to 1880 to pretty recent. And you can see it does fluctuate around a lot, and in the last period of time, it seems to have been increasing by a certain amount there. Now, this data, of course, has come under enormous scrutiny. These three groups independently took all of the data and analyzed it, and they've put those curves up there. And then people came and said, no, we think you fudged it, and you did all these. So a group at Berkeley, with Rich Muller and many other colleagues, have obtained all of the publicly available data from 26,000 climate stations that have collected data over the years, and they have performed a reanalysis, if you like, of all of that data. This is only 2% of the data, but it's done transparently. They've posted on the web their methodology. They've put all the data out there. Anybody can go and check it and look at it and do whatever they want with it. And guess what? It looks exactly like all the other analyses that are out there that people did very carefully beforehand. So it's fine to ask the question, are you sure that you did this correctly? So people went back. That's what scientists do. They double-checked it. They triple-checked it. They quadruply-checked it. This just shows a little movie of all these temperature stations from that BEST project. So at first, there's very little data, and they've developed some procedures for how to analyze, to calculate the average of the Earth's temperature. There's some tricky things. What you'll see is there are very few temperature stations that recorded data at first, and then more of them became available. This shows only the 2% that they used in that first analysis, but every so you see there just a new one popped in, and you can see these temperature measurements for all this whole interval. Look carefully here. When it hits around 1930, look at this part of the United States, and you will see the dust bowls, which show up during that period. And so this just shows, and of course what the group has been looking for here is if you have two stations that are right adjacent to each other, you don't want to treat them as independent information. You're trying to analyze in a statistically correct way across the whole thing, and so on. So you can just see this movie. It'll just go for a little bit more. We're getting close to, it's a little too slow, isn't it? But it's kind of fun, actually. You can trace the development of how people measured things by when these stations show up and stuff. Dust bowls. Yeah, that was them. There. Okay. So, okay. Now, you can do models of the temperature that have been not just measurements, but models of the temperature, not just measurements. And this red curve shows the models. Now, it's true that the models are models, and you try to put into them everything that you know how to put in. And people will make many different models, and they contain things differently. And there's a whole institute at Livermore Lab that just takes all of the models and tries to average them in an intelligent way. Because there's a lot of them, and it's a big project to do that, and that's where these red curves kind of come from. And you can see stuff like people will say, what about the volcano? Here's the volcanoes, they're accounted for, don't worry. And sure, volcanoes will momentarily change the temperature a little bit. You can see that. Here shows you what happens if in the models you simply leave out the atmospheric CO2. You leave out the human activity. If you just leave that out, then this is what the models say would be happening during this period of time. And I want to emphasize the models include all the things that you hear about, like sunspots and whatever, all that stuff. It's in there. And so the best models we know how to create say that this is what's really happening when we include people emitting fossil fuels. This is what happens when we don't. And this difference is what's happening due to the CO2 being emitted into the atmosphere. Now, it is true that the effect is relatively modest so far. That's because the CO2 has increased some. It's approaching 400 parts per million. We haven't quite doubled it yet. And it's going to also take some time at a new configuration. And that will be warmer ultimately, and it'll take a little bit of time for it to reach that new temperature. And so, we can, of course, wait for a while and see where it goes. That's an option. And we'll talk about that momentarily. Now, another thing that we need to do, one reason I put this thing into my thing recently is in one of my hats that I wear that, Paul thanks me for doing. I went one day not too long ago to visit with some folks at the Heritage Foundation, and I sat down and talked with them about stuff, and it was a nice conversation. And at one point, one of the folks said to me, I would really like to see us burn all the coal to get energy. He thought that was a good thing to do. And so I went back and asked my colleagues at Berkeley, what do we know about what happens if we just burn all of the coal? And so that's about 5,000 gigatons total put into the atmosphere. So you remember, we're emitting about 30 gigatons a year, and about 15 stay in there. So, there's some limits there. And so these are just some estimates of what happens. And this is what you have to realize, is that if you put CO2 into the atmosphere, and then you stop doing it all of a sudden, you just stop, and you say what happened. So it's at some high level. At first, CO2 will go down because it goes into the ocean. It changes the pH, does stuff like that. Okay. And then eventually it does come back again, but this is because of the geological processes that I talked to you about. This is the really long cycle where there are volcanoes, and the volcanoes spew out stuff, and then that comes back into the ocean, and then that makes sedimentary rock, and eventually it becomes rock. That's a very slow process. It does happen. So that's the recovery times are long. And of course, these light gray curves are if you only emit a total of 1,000 gigatons into the atmosphere. This is what happens if you do 5,000. So the models say that if you do 5,000, basically you take the temperature up about 7 degrees, and it comes back maybe 100,000, 200,000 years later. In a long time. This is what happens if we emit somewhat less. Is it goes up some, but it comes not as much, just a couple of degrees. So, this is ice-free Earth. Now, people want to know, what are the range of impacts? Everybody wants to know what are the range of impacts. And I'll say I've tried to study this question. I've spent a lot of time trying to go in and read the literature, and I can't actually honestly tell you that I know the answer to that question in the same way that I say I could answer for you the question, does an increase in CO2 change the temperature? Your answer is yes. Are we increasing the CO2? Yes. Those are easier questions to answer. The impacts are harder. And the reason the impacts are harder is because there's a lot of feedbacks in the system. I mentioned to you the example of the feedback. As we put CO2 into the atmosphere, it warms the atmosphere. When you warm the atmosphere, some water vapor goes into the atmosphere, which is also a greenhouse gas. That's a positive feedback. But you also could make some extra clouds. Clouds are white. They scatter light. Therefore, there's a negative feedback. And, you know, there's lots of feedbacks. There's a whole slew of feedbacks that some are positive and some are negative, and you try to include all of them. Okay, so let's just be honest and say it's very hard to know what all of the feedbacks are. Here's the thing that you have to worry about. This shows you what would happen, what do we think is the feedback factor, the net feedback factor that occurs. That would show up in this equation as the actual change in temperature is the change in temperature if you double CO2 without any feedbacks over 1 minus what happens if there is a feedback. Okay? And here is a possible range of values for the feedback, a normal distribution. And this reflects what people think is actually kind of a realistic probability distribution. In other words, most likely the feedback factor in the end is around this value of 0.65 or something. And it's got this distribution. The problem is that this delta t over delta t0, 1 minus f, that 1 minus f, if f, for example, is 1, then this becomes 0, and delta t diverges, okay? And this is where the problem is. Because of this equation, this has a funny form to it, where it cuts off relatively quickly on the low temperature side, but it has a long, fat tail on the high temperature side. What does that mean? That means we take our best guess about the feedbacks and we assume some statistical distribution from them, and then it turns out, okay, this is the most probable value a few degrees C, but actually, if you look at this part of the curve, there's a substantial probability that's large for the doubling. In other words, there's a chance that the temperature will go up a couple of degrees, and you know, some stuff will happen that's not so terrific, but everything will be okay. And there's a chance that's true. But there's at least as big, if not a bigger chance, that the change will be quite a bit larger than that, and a 5 and 6 degree change is a big enough one that it induces massive disruption in civilization, in human civilization. I mean, that's the fact. So in a probabilistic sense, in the end, I think any scientist has to say, we don't really know for sure what the total, what the temperature change is going to be, but what we can say to society is there's a good probability, a significant probability, that the change is big enough that the consequences are very large enough that you really have to do something about it. So, at Berkeley Lab, we've been organizing this initiative called Carbon Cycle 2.0, and the goal is to bring the whole laboratory together to work on this problem. And we have projects that range across all of these topics. So I want to give you a quick feel for how to read this diagram. We have here things like energy efficiency, combustion, and so on. Each one of these circles, there's a big group of scientists at the lab that are studying this topic. And in the center of it, in the very center, sits an energy analysis group and the climate modelers. And what we've asked, for example, is for each one of these groups to talk with these two in the middle. And the energy analysts come and have a dialogue, and they say, okay, let's take biofuels for an example, and let's calculate out what would happen if we deployed biofuels. How big could they get? What's the biggest they're likely to be? 10% of transportation fuel, 15%, 20%, something like that. And they take those numbers and they calculate them out, and they also do some other estimates about whether we're going to cause some other resource to be limited and so on. And then they turn to our friends in the climate models and they say, okay, when you make your next climate model, assume that biofuels are present at 15% of transportation fuel and try to create a new regional climate model. And they repeat that with every one of these circles, okay? And that's bringing, in a sense, the entire national lab together to try to work on this problem from many different perspectives. I'm going to take about 5 minutes because I went a bit longer on the history stuff than maybe I intended. I just want to leave you with maybe 3 very important points about the Carbon Cycle 2 project. The first one is efficiency, and I want to remind everybody that efficiency is a great thing. It saves Americans billions of dollars every year. Here's Art Rosenfeld. Art was a student of Enrico Fermi, a very famous particle physicist who decided in the energy crisis in the 1970s to stop doing high energy physics and to work on energy efficiency. And he became a very, very strong advocate for energy efficiency, and he had an enormous impact on the world around him. And I just want to tell you the story, because one of the things he did is he advocated for refrigerator standards. So quickly, we're going to do the refrigerator story, because it's important that you know this. This shows the energy consumption in blue here of refrigerators as a function of year up to the year 1979. And it went up, 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 up. In other words, you got a refrigerator, but it used more energy. And this is the year when the first energy efficiency standard was passed. And then it went down, 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 down because of the energy efficiency standards, because they were making really bad refrigerators that didn't have efficient motors and insulation and stuff like that. And this is the cost of the refrigerator. And guess what? The cost went down for the consumer even as the efficiency improved. And guess what? You even got to buy a bigger refrigerator. It got bigger. The cost went down. The efficiency got better. You did hit a fundamental limit. That is the door of the kitchen. Due to innovation, the doors were enlarged. That's the efficiency story. It's a good thing. A couple more things. When we think about the problem of the solution, ultimately, of the carbon cycle, one thing scientists have to know is the scale of the problem is really, really big, 30 gigatons a year. So we have to think about that. These are the CO2 emissions per year, 30 gigatons. This little bar here shows the top 100 commodity chemicals produced, bulk chemicals, you know, the ones they put in big train trucks and cart them around, okay? The top 100 produced in the world, all added up, okay? And they're 60 times smaller than the CO2 emissions. It's another way of saying that is energy is the biggest industry in the world by an enormous factor. And consequently, any discovery that you make to try to get deployed in the energy space has to be on an enormous, enormous scale. Now, you can capture CO2. I'm not going to go through all the details of this, but one thing that you could do, and I just want to put one number out there. One thing that people do know how to do is to put at the end of a power plant a scrubber that CO2 would go into, and in it is this water, and in there is an amine, and the CO2 binds to the amine very strongly, and it takes the CO2 out. And then later on, you have to release the CO2 and try to put it underground, okay? We could debate whether that's a good thing or a bad thing, but that's an existing technology. It turns out the problem with it is to get the CO2 back out, you have to get the CO2 back out because there's not enough amine to capture all that CO2. You have to recycle it, but the amine. But the problem is you have to boil the water, and when you boil the water, it's about 25% of the power efficiency of the power plant, okay? So that's not a terrific technology, but it does work. But here's an interesting thing. What does that cost? 8 cents a kilowatt hour. Now, I don't know what you pay for your power. In California, at my home, we pay 12 cents a kilowatt hour. Actually, I asked most people this, and they don't know what they pay, actually, in cents per kilowatt hour, because they don't really think too much about their energy use. But at us, it's 12 cents per kilowatt hour up to about 48. It's graded depending on how much energy you use. And so it turns out 8 cents, you know, is that a big number or a small number? It's hard for me to say. What I can say is that in the end, if you really want to take existing technology and solve this problem, you can probably do it in the neighborhood of 10 to 12 cents a kilowatt hour. If you want to pay that amount, we could probably just do today's technology and implement it, and it could work. So that's just one thing to say. Now, I have some other things which I'm going to skip over here because I feel I've gone way too long. There's one more point I really, really want to make, though. These are some things we have to pass over. I apologize. Here we go. Please take a look at this plot. I'll run it a couple of times. This shows the developing world, and what you see here are some circles, which are, you can't really see these numbers too well, but they're the years going by. And the circles are different countries, okay? And the size of the circle is the population. And this graph shows the CO2 emissions, and this one is the income per person, okay? Income per person, CO2 emissions, and that goes as a function of the year. Let me just try to replay that if I can. And what you see here is there's the US, that was the Great Depression, and the circles going up, 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 and you see all these circles here and other ones. And what I want you to see here are a few different things. Look at these circles. These are countries that have the same income per person, but use maybe a fifth of the CO2 that we do. It's just, sometimes people will say, well, my use of energy is correlated totally with my economic productivity, and if you start messing with this stuff, we'll be in big, big trouble. The fact is, you can get energy many different ways, some of which don't involve using CO2. So it's quite possible for us to have an energy-rich environment that is not using as much CO2. It's proven. But look at all these circles. Here's India, here's China, and here are all these other circles. These circles here, all these are people who live on, there's 2 billion of them, who live on $2 or less a day. And these people, of course, like any other person in the world, are hoping that their children have a better life than they do, and they're going to fight every day of their lives to have a better life, as well they should. It turns out that if you think about the total global carbon picture over decades, what we do, okay, we have a very big circle that's very high on here, and what we do does matter some, but it turns out what all these circles do, are they going to go like this or like this, is actually the question that will determine whether we put so much CO2 into the atmosphere that we make an absolutely enormous change in the temperature or only a relatively modest one. And therefore, what happens in the developing world with respect to how they use energy is just as important to us as it is to them. And that's something that's very important for everybody to understand. We need to help the people in the developing world have access to energy in a way that helps them develop in a good way, and that's one of our huge obligations. At Berkeley Lab, we have a lot of projects, I'm not going to go through them, that work in this area, and we're establishing, hopefully this fall, an institute that will be dedicated specifically to this topic. I don't think I'm going to say too much about these other topics because I feel like I've gone for quite a long time, and what I want to do is just kind of give you one last statement about the Carbon Cycle 2 initiative. I want to emphasize that in each one of these circles, there's a whole research topic, a whole way of thinking about this problem, but that could happen any place. What I think is special about this particular initiative is the centerpiece here, in which we're trying to have a common energy analysis for every one of these, which ultimately will feed into a regional climate model. For example, you might ask the question, what would happen if we deployed solar cells? And this is the last question. I'll just give you a feeling for the type of thinking that's going on. Let's say we deployed them enough that they made a big difference. That might be, say, 50 million acres. And maybe we would do 50 million acres someplace out in the desert. The desert, it turns out, is kind of tan-colored, so it's kind of whitish, right? And we would be replacing it with black solar cells, black, okay? So now they're going to be absorbing all that light, and they're going to be black, they're going to warm things up locally. You know, what's the effect of that? Well, it turns out, okay, that will induce some regional local warming, and it will change the local climate patterns in that part of the country where that's going on. We'll change a little bit from that. So we're trying to take that into account. But then you could say, well, how does it impact the carbon cycle? Well, it turns out, actually, if you think about all the fossil fuel that you're removing from the energy equation, on net, they would be extremely net beneficial to have those. But there is this small correction factor, and actually in the world of changing energy, this is the one thing I want to, the very last thought that I want to leave you with on this is, the issue that we face is that because energy is the largest industry in the world, what we found is that our energy is the first thing that we're doing as people that's changing the planet. It's the first thing that we're seeing that effect. What it means is that anything that we do change to will also be very big and therefore is also likely to have consequences. And that's why we have to become more sophisticated in our thinking. And really this challenge of carbon cycle 2, the emphasis should be really on the word cycle. Because if we think about the living systems, which give us an example, life itself all around the planet, as it has evolved and developed, life at one point in time became global in its scope. And you'll remember that everything operates in life on the basis of cycles. There's a carbon cycle, a nitrogen cycle, everything is a cycle. And you say, why is it? Why is it that nature operates everything on cycles? Well, the answer is because if you only do half a cycle, like taking a fossil fuel and burning it to CO2 and water, but not taking the CO2 and water and bringing it back to hydrocarbon, if you only operate half the cycle, but you're global in scale, you're going to run into a big problem eventually. And that's why our thinking needs to change to become one of cycles in all of our technologies over time. Carbon will be the first one, but ultimately, hopefully, there will be many other cycles. And I'd like to thank you for your attention tonight.